Welcome to Sleepy Harbour. Tonight we are going to slow down together and spend some time inside one of the quietest, most extraordinary things your body does. The work your brain takes up the moment you stop paying attention to it. While you lie here, settling into the dark, your mind is about to begin its night shift. Not resting, not switched off, working. Sorting through everything you gathered today and deciding gently and carefully what to keep. You do not need to know anything about neuroscience to listen. There is nothing to study here, nothing to memorize, no test waiting for you in the morning. If half of what I say drifts past you like a boat slipping out of the harbor before you quite see its name, that is exactly as it should be. You are allowed to follow only the parts that want to be followed. The rest can wash over you like the tide. If you feel like it, before you let go entirely, you might leave a small note in the comments. What time it is where you are and the name of the place you are listening from. It is a quiet thing, knowing that somewhere out there, another person is lying in the dark at the same hour, listening to the same slow voice. A small harbor full of small lit windows. And now take a slow, deep breath. In through the nose, gently. And let it go all the way out, like a long sigh you have been holding since this morning. Wherever you are, a bed, a couch, a chair by a window, a train carriage humming through the night, let yourself settle in. Let your shoulders come down from wherever they have crept up to. Let your jaw soften. Let your hands lie open. Thank you for joining us here at Sleepy Harbour. Let us begin. I want to start with something you already know in your body, even if you have never had words for it. You have lived this. Everyone has. You learned something during the day. A name, maybe. The name of someone you have just met, said warmly across a table, repeated once so you would not forget it. And you do not forget it, not at first. You hold it for an hour, for an afternoon. And then somewhere in the evening it begins to thin, the way mist thins, and by the time you are reaching for it again the next morning, it has gone soft at the edges, or gone entirely, and you are left with the shape of a person and a small embarrassed hole where their name used to be. Or it is the opposite. You struggle with something all day, a tune you cannot quite play, a problem you cannot quite crack, a list you keep getting wrong by one stubborn item, and you go to bed defeated. And in the morning, without trying, without even thinking about it, the thing is simply there, easy, as though someone came in the night and tidied it for you while you slept. People often think the slipping away is a personal flaw, a bad memory, a weakness, something other people do not suffer from, and people think the overnight tidying is luck or coincidence or just a fresh start. But neither of those things is luck, and neither of them is yours alone. They are the two visible edges of one hidden machine. The same machine, running every night in every sleeping head on this turning planet. It has been running since long before anyone had a word for it. It is running in you right now, just beneath the surface, waiting for you to step out of its way. So let me tell you what that machine is actually doing. Because it is far stranger and far more beautiful than rest. Here is the first thing. And it is the kind of fact that the first time you really hear it makes you sit very still. While you sleep, your brain replays your day. Not in dreams, not in pictures you remember. Underneath all of that, it takes the things that happened to you and it runs them again, in sequence, in the same order they happened. But it runs them fast, compressed, somewhere between 10 and 20 times faster than they happened in real life. A walk that took you 20 minutes is relived in a second or two. Your brain, in the dark, hits fast forward on your own day, over and over, replaying the path you walked, the route you took, the order of the things you touched. We know this because of a beautiful experiment with rats back in 1994 by two scientists named Matthew Wilson and Bruce McNaughton. There are cells deep in the brain, in a little seahorse-shaped structure we will get to know very well tonight. And these particular cells are called place cells. They are like a tiny internal map. When a rat runs through a maze, certain place cells fire as it passes one corner, others fire at the next turn, others at the far wall. A whole sequence of little flashes that together trace the shape of the journey. One cell for here, another for there. A string of lights laid down along the path the animal actually walked. And what Wilson and McNaughton found is this. When the rat went to sleep, those very same cells fired again, in the very same order. The brain was rerunning the maze, tracing the exact route it had walked while awake, corner by corner, wall by wall, but compressed, sped up, 10 to 20 times faster than the real run. The little lights flickering through the whole journey in a heartbeat. Again and again. The animal lying perfectly still, eyes closed, going nowhere, and inside, running the maze on fast forward all night long. This is one of the most carefully tested findings in the whole science of memory. It has been shown again and again by many different hands, in many different laboratories. The sleeping brain rehearses the waking day. It practices, it rewalks the path. And here is the part that turns this from a curious fact into something with real weight. There is a particular electrical signature that goes along with this replay, a fast, sharp little burst of activity we will name properly later. And scientists found a way in animals to reach in and silence just that one signature, just the replay. Without disturbing the sleep itself, the animal still slept soundly, still rested, still passed the night in apparent peace. They took away only the rehearsal, only the rerunning of the day. And when they did that, the memory did not stick. The learning that should have settled in overnight simply did not. Block the replay, and the memory slips away. So the slipping away you have felt, the name gone soft by morning, there is a version of that which is not bad luck and not a flaw. It is what happens when the night's rehearsal does not run or does not run well. Hold on to that thought gently, because we are going to come all the way back to it. For now, just let it sit. The brain reruns your day to keep it, and if the rerun is taken away, the day washes out. We will get to exactly how that rerun works, and exactly how they switched it off, a little further into the night. For now, breathe and let the strangeness of it settle. Your day replayed in fast forward while you do absolutely nothing but lie here and let go. Now, to understand why your brain bothers to do any of this, why it goes to all the trouble of rerunning your day at 20 times speed in the middle of the night, we have to talk about something that sounds technical, but is really very simple. It is the most important idea of the whole evening, and once you have it, everything else tonight will rest on top of it, like a house on good ground. Your brain does not have one memory store, it has two, and they could not be more different from one another. The first one is fast. It is that little seahorse-shaped structure I mentioned. There are two of them, in fact, one on each side, curled deep in the middle of your brain, and the name for them is the hippocampus. Hippocampus simply means seahorse in the Old Greek, because that is the shape early anatomists thought it resembled when they first held one in their hands. The hippocampus is your brain's fast learner. When something new happens to you, can a name, a face, a place you have never been, the exact words someone said that landed hard, It is the hippocampus that catches it, and catches it quickly. It does not need repetition. It does not need to be drilled. It can grab a whole experience in a single pass and hold it. Think of it as an inbox, a bright, fast, eager inbox sitting just inside the door, catching everything that arrives through the day. A face here, a fact there, a conversation, a turning, a smell, a feeling. It takes them all in, fast, no questions asked. But an inbox has limits, and this one has two. It is small. It cannot hold very much at once. Its capacity is genuinely limited, and the more you cram into it in a day, the more crowded and jostled everything inside it becomes. And it is fragile. The things in the inbox interfere with one another. A new arrival can shoulder an older one aside, blur it, knock it loose. This is why, when you meet 7 new people in a row, the first 3 names are already smudging together by the time you reach the 7th. The inbox is fast, but it is shallow, and it is easily disturbed. It was never built to keep things forever. It was built to catch them. And then there is the second store. This one is the opposite in every way. It is vast, enormous really, a sprawling territory spread across the great wrinkled outer sheet of your brain, the part called the neocortex, or just the cortex. The cortex is your slow learner. It does not grab things in a single pass. It builds knowledge gradually, layer by layer, weaving each new thing into the great web of everything you already know, which is exactly why it is so good at holding things for a lifetime. The skills you will never lose. The facts that have become simply part of you. The deep, settled, unshakable knowledge of who you are and how the world works. All of that lives out here in the slow, patient, immense archive of the cortex. So that is your two-store brain. The hippocampus, fast, small, fragile, eager. The inbox by the door, and the cortex, slow, vast, patient, permanent. The archive in the deep stacks where things are kept for good. This way of seeing it has a name. Scientists call it the complementary learning systems model. Complementary because the two stores complete each other, each one good at exactly what the other one cannot do. It was laid out in full in 1995 by 3 researchers, James McClelland, Bruce McNaughton, yes, the same McNaughton from the Sleeping Rats, and Randall O'Reilly. And it is one of the most cited, most leaned upon ideas in the whole science of memory, a fast, fragile catcher, a slow, durable keeper. You need both. A brain with only the inbox would forget everything by the next day. A brain with only the archive could never learn anything new fast enough to survive a single afternoon. So you carry both, and they hand things to one another. And now perhaps you can feel where this is going, because if the inbox is small and fragile, and the archive is where things are kept for good, then at some point, the things worth keeping have to make the journey from one to the other. They have to be moved out of the crowded, jostling inbox before the next day's flood arrives and shoulders them out. They have to be carried carefully into the deep, quiet stacks of the cortex and filed where they will last. When does that happen? When is there time and quiet and space enough for the brain to do that careful moving without 1,000 new things pouring in through the door every second? At night, while you sleep. That is what the replay is for. That is why your brain reruns your day at 20 times speed in the dark. It is reading the day's catch back out of the fragile inbox and carrying it piece by piece into the permanent archive. The rehearsal is a transfer. The fast forward is a filing. This process, the slow migration of a memory out of the hippocampus and into the wider networks of the cortex, has a name too. It is called systems consolidation. And it does not happen all at once. It unfolds over days, over weeks, sometimes over years, a memory becoming gradually less and less dependent on that little seahorse inbox and more woven into the great cortical archive, until one day it can stand entirely on its own, until even if the hippocampus were damaged, the memory would survive because it has been moved out, fully filed, kept somewhere safer. We can actually see this. Recent memories lean on the hippocampus and falter if it is harmed. But old, remote memories, the ones that finished their migration long ago, survive out in the cortex, where they have made their home. The memory grows up in a way. It leaves the fragile inbox behind and goes to live in the deep stacks. And here is the most beautiful refinement of all, and it changes how you should picture this whole night. For a long time, people imagined memory as something passive, as though the brain were a recording device, and sleep was simply the moment the recording got saved to a hard drive, quietly, mechanically, the way a file copies from one folder to another. Press, save, wait, done. But that is not what is happening. The brain is not copying a recording. It is actively reaching back into the inbox, pulling each memory out, replaying it, and rebuilding it inside the archive. It is reconstruction, not duplication, reprocessing, not recording. The memory that ends up filed in your cortex is not a photocopy of the one that arrived in your hippocampus. It has been handled, turned over, woven in, slightly remade in the moving. This idea has a name as well, and a pair of scientists most closely tied to it, Jan Born and Susanna Diekelman, who in 2010 laid out what is called the active systems consolidation hypothesis. Active, that is the word that matters. Your sleeping brain is not a passive recipient of the day, holding still while files copy themselves across in the background. It is an active participant. It chooses, it reruns, it rebuilds, it decides what to carry and what to let dissolve. It is, in the truest sense, doing something, quiet, invisible, tireless work, at the very hour you believe you are doing nothing at all. So this is the picture I want to leave you holding as we pause. A fast little inbox by the door, catching everything, fragile, easily crowded. Your hippocampus. A vast, slow archive in the deep, where things are kept for a lifetime. Your cortex. And every night, in the dark, a patient hand reaching into the inbox, pulling out the day's catch, rerunning it at 20 times speed, and carrying the keepers, one by one, back into the stacks to be filed for good. The night shift, the archivist who works while you rest. And you do not have to do a single thing to make it happen. That is the gift of it. You do not have to try or concentrate or remember to remember. You only have to sleep. The archivist takes it from there. Let us pause here for a moment. Take a slow, deep breath. In, gently all the way down, and let it go, slowly, completely. Notice how your body has begun to settle into wherever you are lying. Notice the weight of you, held by the bed beneath you. Notice the quiet in the room, and underneath the quiet, the soft fact that your own brain is already beginning this work tonight. The inbox by the door, the archive in the deep, the patient hand moving between them. You do not need to remember any of the names. You do not need to hold the seahorse or the cortex or any of it. Let it all loosen. And when you are ready, in no hurry at all, we will continue together, and I will tell you exactly how that little maze gets rerun in the dark, and the astonishing way scientists learn to listen in on it, and the precise three-part choreography of brainwaves that does the filing. There is so much more, and all of it is gentle, and all of it is happening in you right now. For now, just breathe, just rest. The archivist is already at work. Let us begin again, softly, with the thing that first made the scientists lean in close. It was a maze, and it was rats, and it was the early 1990s. Two researchers, their names were Wilson and McNaughton, had taught rats to run a little track, and they were listening very carefully to certain cells deep in the rat's brain. These cells live in the hippocampus, the small seahorse-shaped store by the door, and they have a lovely name. They are called place cells. A place cell is a neuron that fires when the animal is in one particular spot, and only that spot. One cell for the corner, another for the bend in the track, another for the far end. As the rat runs the maze, the place cells light up in a sequence, like a row of small lamps, switching on one after another down the length of a hallway. Corner, bend, straight away, end. A little song of places, sung in the order the rat moved through them. And then the rat went to sleep. Here is the thing they found. Here is the thing that is so quietly astonishing that it is worth lying still for. While the rat slept, those same place cells fired again, in the same order, the very same sequence, corner, bend, straight away, end, playing back inside the sleeping brain as though the rat were running the maze all over again, in the dark, with its eyes closed, going nowhere at all. But not at the speed it had run. The replay came compressed, sped up, roughly 10 to 20 times faster than the real running had been. The whole journey down the hallway of places flickering past in a fraction of the time it had taken to live it. Imagine watching a recording of your afternoon walk, but the recording rushes by at 20 times the pace, a whole hour of strolling crammed into a few minutes of flickering light. That is what the sleeping brain was doing, taking the day's path and running it back at a sprint over and over while the body lay perfectly still. This is what the scientists came to call hippocampal replay, the brain replaying experience at high speed during sleep. And it has been found again and again in study after study until it is one of the most solid, most trusted findings in this whole field. The little maze rerun in the dark. The day rewound and rushed back through again and again while you sleep. Let that settle for a moment, because it changes what sleep is. It means the sleeping brain is not a brain that has switched off. It is a brain that is busy. It is reaching back into the day it just had and running it again, faster, as if to ask, what happened here? What mattered here? What shall we keep? The archivist, you see, does not file blindly. First, it rereads. It reruns the day's catch at 20 times speed, and in that fast, flickering rereading, the decision begins about what gets carried into the deep. And here is the line that should make you lean in, even as you are growing heavy and warm and ready to drift. Because the obvious question, the question a good scientist cannot leave alone, is this: is the replay just an echo? Just the brain idly murmuring to itself, a leftover hum from the day signifying nothing? Or is the replay the actual filing, the very act by which the memory gets saved? There is a way to find out. A hard, clever, almost unkind way. You wait until the sleeping brain begins one of these bursts of replay. There is a particular electrical signature that comes with it, a fast little flourish in the recording. And at the precise moment it begins, you interrupt it. You block it. Not the sleep itself. You let the animal sleep on undisturbed, breathing slow. You block only the replay. You reach in and you stop the rerunning of the day while leaving everything else exactly as it was. And when you do that, when you block the replay and let everything else proceed, the memory does not get saved. The benefit of the night vanishes. The animal that should have woken knowing the maze a little better wakes not knowing it. Same sleep, same hours, same darkness. But the filing never happened because the rereading was stopped. I want you to hold the weight of that gently, the way you would hold something small and alive. It means the replay is not an echo, it is the work itself. Block the rewind and the memory simply does not make it across. The brain has to rerun the day in order to keep it. The night shift is not optional decoration. It is the only road into the archive, and if you close that road, the day's catch is lost by morning. Exactly the way a fact you were so sure of last night can be gone, soft and slippery and untraceable by the time the light comes. You have felt that. Everyone has. The thing you knew dissolved overnight into the place where lost things go. Now you know there is a machine behind that loss and behind the keeping too. The replay either ran or it did not. So, we have the rewind, we have the proof that the rewind is the filing. But none of that has yet told us where the memory goes or why it has to go anywhere at all. Why not simply keep it where it landed in the little seahorse by the door? Why the whole nightly journey from one place to another? For that, we have to talk about the two stores and why the brain, in its long wisdom, chose to build two of them instead of one. Think of it this way: when something happens to you, a face, a name, a corner of a street you have never seen before, it has to be caught, and caught fast. You cannot take a week to slowly learn the name of the person standing in front of you right now. You need to grab it in one go, immediately, on first contact. So the brain has a store built exactly for that. The hippocampus. Fast. Eager. It learns in a single shot. One exposure, and it has the trace. This is your inbox, the little tray by the door, where the day's new arrivals land. Quick, bright, immediate. But fast learning comes at a price, and the price is fragility. A store that learns in one shot is a store that is easily overwritten. New things keep landing in the inbox all day long, and each new arrival can smudge the ones already there. The inbox is small and it is crowded and it is prone to interference. One memory blurring into another, the way the names of two people you met at the same party can bleed together until you are not sure which is which. The hippocampus is brilliant at catching. It is terrible at keeping. It was never built to hold things for a lifetime. It was built to hold things until they could be filed somewhere safer. And that somewhere safer is the second store, the neocortex, the vast, deep archive that wraps around the outside of your brain. This store is everything the inbox is not. It is enormous, room for a lifetime of knowing. It is stable. Things filed here are not easily smudged by the next day's arrivals, but it is slow. The cortex does not learn in one shot. It learns the way a path is worn across a meadow, not in a single crossing, but by being walked and walked and walked again until the way is clear and permanent and will not be lost. The archive needs repetition. It needs the same memory presented to it many times before it will accept the trace and hold it for good. Now you can see the beautiful problem the brain has solved. It needs to learn fast, so it has a fast store. It needs to keep things stably for a lifetime, so it has a slow store. But fast and slow cannot live in the same place. The very thing that makes one good makes the other impossible, so the brain built both and gave each its proper job, and then it needed a way to move the day's catch from the one to the other. From the fast, fragile inbox where things are caught but cannot last, into the slow, vast archive where things last but cannot be caught quickly. Scientists gave this two-store arrangement a name. They called it the complementary learning systems model. Complementary because the two stores complete each other, each supplying exactly what the other lacks. It came from three researchers, McClelland, McNaughton, and O'Reilly, and back in the mid-1990s, and it has become one of the most leaned-on ideas in all of memory science. Two stores, one fast and frail, one slow and deep, and a nightly ferrying of the keepers from the first into the second. That ferrying has a name too, and it is a plain one: systems consolidation. It simply means the slow process by which a memory that began its life dependent on the hippocampus, held in the little seahorse by the door, becomes, over days, over weeks, over sometimes years, woven instead into the wide networks of the cortex. At first, the memory lives in the inbox, and if the inbox were damaged, you would lose it. But once it has been ferried across, once it has been walked into the archive enough times to wear its path, it no longer needs the seahorse at all. It lives in the deep. It has become a remote memory, a permanent one, safe even if its first fragile home were harmed. This is why your oldest memories are the most secure ones. They have long since left the inbox and settled into the stacks, filed and refiled, until nothing short of real damage could shake them loose. And sleep is when the ferrying happens. Sleep is when the hand reaches into the inbox, lifts out the day's keepers, reruns them at 20 times speed, and carries them, trace by trace, down into the archive to be walked into the path that makes them last. For a long time, people imagined this filing as a passive thing, as though the memories simply drained from one store into the other overnight, the way water finds its level. No effort, no choosing, just a quiet settling. But that is not what it is. The newer understanding, the truer one, gave it a sharper name: active systems consolidation. Active because the memories are not draining anywhere. They are being lifted and replayed and redistributed, chosen, reread, carried on purpose by a brain that is doing real work in the dark. This idea was set out most clearly by two researchers named Diekelman and Born, who gathered the evidence and made the case that the sleeping brain is not a storehouse passively leaking from one room into another, but an archivist actively reprocessing the day, rerunning it, deciding, filing. A reprocessing, they said, not a recording. And that single word is the whole turn of it. A recording would just be played back, unchanged, a copy laid down and left alone. But a reprocessing means the memory is handled, worked, turned over in the hand and set down somewhere new. The thing that comes out the other side of the night is not quite the raw thing that went in. It has been read and sorted and carried and relayed into the deep. That is what is happening in you right now as you lie here growing heavier. Not a tape playing, a hand working. A patient, tireless, wholly ungrudging hand, moving the day from the place where it could not last into the place where it can. Let us pause here again, just for a breath. Take a slow one, in through the nose, all the way down to the bottom of you, and let it go without any hurry at all. Notice how much lower you have sunk into the bed since we began. Notice the warmth gathering in your hands, in your shoulders, in the long muscles of your back, as they finally let go of the day. There is nothing for you to carry now. The inbox by the door, the archive in the deep, the fast store and the slow, the ferrying between them. You do not need to hold one word of it. Your brain already knows how. It has always known. It is already beginning quietly, in the dark, to lift the keepers from today and walk them home. And when you are ready, in no hurry whatever, We will go on to the astonishing way the scientists learned to listen in on the filing itself, and the three brainwaves that move together in a precise and tender choreography to carry each memory across. For now, only breathe, only sink. The archivist is already at work and asks nothing of you at all. There was a rat running a maze. This is where the science begins, and it begins with something so ordinary, a small animal, a corridor of turns, the smell of wood shavings and the distant promise of a reward, that it is easy to miss how strange what happened next actually was. In 1994, two neuroscientists named Matthew Wilson and Bruce McNaughton were doing something that had never quite been done before. They had placed tiny electrodes, thinner than a human hair, near the place cells in the rat's hippocampus. Place cells are neurons with a particular and wonderful property. Each one fires when the animal is in a specific location. This cell wakes up here, at this bend in the corridor. That cell lights up only there, near the northern wall. The cells collectively form a kind of living map, a neural signature of the animal's journey through space, each footfall annotated in the language of electricity. Wilson and McNaughton recorded which cells fired and in what sequence as the rat made its way through the maze during the day. And then the rat went to sleep. What they found, listening in on those same cells in the hours that followed, has been called one of the most robustly replicated discoveries in all of memory neuroscience. The place cells fired again, not randomly, not in scattered bursts with no connection to the day's experience. They fired in the same sequence, the same order, the same cells, the same map of the journey. As the rat lay still with its eyes closed, dreaming whatever rats dream, the brain was replaying the maze run. This alone would be astonishing enough. But the detail that truly stops the breath is the speed. The replay was not happening in real time, as though the sleeping brain were rewinding a tape and playing it back at the same pace the journey was lived. It was compressed. The sequence that took minutes to run in the world was rerun by the sleeping brain in seconds, roughly 10 to 20 times faster than the original. Your brain, in other words, does not just replay your day. It hits fast forward. Think for a moment about what that means, because it is worth sitting with. Everything you did today, the morning light falling across the kitchen table, the conversation you had in the hallway, the route you took to wherever you needed to be, the names you tried to hold on to, the face of someone who mattered. All of it is being rerun at high speed somewhere behind your closed eyes, not because you are choosing to review it, not because anything is being asked of you, but because the hippocampus, that fast learning inbox of the brain, has flagged those sequences for transfer, and the transfer requires a rerun. The archivist does not simply move a file. The archivist reads it again, quickly, on the way to the shelf. That finding, Wilson and McNaughton, 1994, published in the journal Science, opened a question that scientists have been working on ever since. The replay is there. You can measure it, you can watch it, you can even predict from the day's activity which sequences the sleeping brain will choose to replay. But what does the replay actually do? What is it for? The answer, when it began to come, came in two parts. The first part is this: replay is not just a curiosity, not just a fascinating echo, it is the mechanism of transfer. The rerunning of the sequence in the sleeping hippocampus seems to be precisely how information is moved from that fast, high plasticity, fragile short-term store into the slower, deeper cortical networks where it can last. The hippocampus reruns, and as it reruns, the cortex listens. The same sequence, repeated fast and repeatedly, begins to etch itself not just in the inbox but in the archive. A memory that was held only in one place, precariously, starts to be held in many places at once, distributed like a story told so many times that everyone in the village knows it, burning it into the deep, trace by trace, replay by replay. The second part came from a discovery about the direction of replay. In 2006, neuroscientists David Foster and Matthew Wilson again, still listening at the same cellular level, found something unexpected. Replay does not always run forward. After an experience, place cells do not only fire again in the same sequence the animal traveled, sometimes the sequence runs backward, from the end of the maze to the beginning, from the reward backward through all the choices that led to it. This reverse replay is thought to help the brain calculate something specific, the path that mattered. When you replay a journey in reverse, you are, in neural terms, working backward from the outcome to the decisions, a form of internal credit assignment, the sleeping brain teaching itself which choices were worth making and in what order. It is not reviewing what happened, it is reviewing what worked. Forward replay to cement the journey, reverse replay to understand it, both happening in compression while the animal sleeps. Now, if replay is truly the mechanism, if it is the actual act of transfer and not merely a side effect, then there should be a way to test it directly, not just to observe it, but to interfere with it, to reach in and silence the replay signal and see what happens to the memory. This is exactly what Gabrielle Girardeau and her colleagues did in 2009. The experiment, published in the journal Nature Neuroscience, targeted a specific electrical signature that accompanies replay in the sleeping hippocampus. These signatures are called sharp wave ripples. They are bursts of fast electrical activity, very fast, oscillating between roughly 80 and 200 times per second, that erupt in the hippocampus during deep sleep, and it is within these ripples that the place cell replay sequences are embedded. The ripple is, in a sense, the carrier wave of the replay, the transmission pulse that sends the message. Girardeau's group developed a way to detect these ripples in real time, as they were actually occurring, and immediately cancel them out with a precisely timed counterpulse. The rats still slept. Their sleep architecture looked normal, the overall pattern of deep and lighter phases still intact. The only thing removed was the ripple itself, that brief burst of fast activity, that specific messenger signal. The result was unambiguous. The rats that slept without their sharp wave ripples intact forgot what they had learned, not partially, not in some subtle way that required careful statistical analysis to find. They forgot in a way that clearly impaired their ability to navigate the maze on the following day, while rats whose sleep was disturbed in other matched ways but whose ripples were left intact did not show the same impairment. Block the replay, lose the memory. It is worth pausing here to be honest about something the science insists on. This experiment was done in rats. The rat's hippocampal machinery is remarkably similar to ours. The place cells, the sharp wave ripples, the architecture of the replay. But a finding in rats is a finding in rats, and the step to human brains, while strongly supported by converging evidence, is inferred rather than directly demonstrated in the same controlled way. The researchers and the scientists who followed them are careful about this, and so should we be. What we can say is this: the mechanism exists, the evidence is strong, and everything we know about human memory from human studies points in the same direction. The ripple is not incidental. The replay is not a dream echo with no function. It is, as best we can tell, the act of filing itself. Take a moment to let that settle, because what it means is not abstract. It means that the forgetting you have experienced, the name you held all evening and could not find the next morning, the detail from a lecture that was there and then was not, the word you were certain you had before you slept, is not a mystery of the mind, not a flaw, not a failure. It is, quite often, the story of a signal interrupted, a replay that did not complete, a ripple that was too shallow, a night that was too short or too broken to let the archivist finish the route. The inbox had the message, the transfer simply did not run. Now we have to go deeper because replay is only the beginning of the answer. Knowing that the hippocampus replays during sleep tells you what is being transferred. It does not yet tell you how the sleeping brain organizes the replay so that it lands correctly in the cortex, in the right places at the right moments, in a way that actually changes the physical architecture of the memory. For that, you need to understand something about the electrical weather of deep sleep. And the electrical weather of deep sleep, it turns out, is not random. It is not noise. It is a precisely choreographed set of 3 rhythms, each one nested inside the other like Russian dolls, each one playing a different role in the same extraordinary process. The outermost rhythm is the one you would see first if you were watching a brain in deep sleep on an electroencephalogram, the instrument that measures the brain's electrical activity through sensors placed on the scalp. In deep, slow-wave sleep, the brain generates what are called slow oscillations. These are big, sweeping waves, slow and stately, cycling roughly 3/4 of a time per second. Not 3/4 of a second between peaks, 3/4 of a cycle in a single second, which means each full wave takes a little over a second to complete. In human terms, this is almost geological in its slowness, the kind of rhythm you could tap your finger to and still feel the pause between each beat. Each slow oscillation has 2 phases. There is the down state. During the down state, most of the cortex goes almost silent. The neurons stop firing. There is a hush, a kind of collective breath held. If you were watching on that electroencephalogram, you would see the line dip low and hold there for a moment, the electrical flatness of a mind briefly gone quiet. Not dead, only still. And then the upstate arrives. During the upstate, the cortex suddenly blooms back into activity. Neurons fire together, a wide and coordinated excitation sweeping across the prefrontal cortex and rippling outward, a wave of availability, a window of possibility. The line on the electroencephalogram climbs, and something in the brain is briefly, very briefly, more ready to receive than it usually is. These slow oscillations do not arise randomly. They are organized, generated in the prefrontal cortex, and sent traveling across the brain in a direction that follows loosely the path from the front to the back, from the newer architecture toward the older, from the regions that manage and supervise toward the regions that specialize and store. The prefrontal cortex in deep sleep is something like a conductor, not choosing what to play, but setting the tempo, organizing the timing, creating the windows within which everything else happens. Now, nested inside the slow oscillation, specifically timed to ride the crest of the upstate, to fire precisely in the moment of maximum excitability, is the second rhythm. Sleep spindles. If slow oscillations are the long, slow tide, sleep spindles are the waves that ride it. They oscillate much faster, between roughly 11 and 15 times per second, and they appear on the electroencephalogram as brief bursts, waxing, then waning, that last only a second or two before disappearing again, waxing, waning, gone. Then another, like little surges of electrical weather, each one arising and subsiding in the time it takes to breathe in and breathe out. They are generated by a specific structure called the thalamic reticular nucleus. The thalamus is a region sitting near the center of the brain, a relay station and gatekeeper of enormous importance. Almost everything you perceive and most of what you think passes through or near it. The thalamic reticular nucleus is a thin shell of inhibitory neurons wrapped around the thalamus like a net, and during deep sleep it falls into a particular kind of rhythmic interaction with the rest of the thalamus that produces these spindle bursts, sending them upward into the cortex and timing them, as though by design, to arrive precisely in the upstate of the slow oscillation. Why does the timing matter so much? Because nested inside the sleep spindle, timed to its own crest, squeezed into the narrowest window within the window within the window, is the third and innermost rhythm, the sharp wave ripple. The same ripple that Girardeau proved was necessary, the same fast burst between 80 and 200 oscillations per second that carries the hippocampal replay sequences. The ripple is the innermost doll, the spindle is the middle doll, the slow oscillation is the outermost doll, and they nest with a precision that still astonishes the scientists who have measured it, one inside the other, synchronized to arrive together at the moment the cortex is most open to receive. The slow oscillation opens a window, the spindle refines the window, focuses the excitability, prepares specific cortical circuits for input. The ripple inside the spindle delivers the replay, the compressed rerun of the day's experience, fired across the synaptic gap from hippocampus to cortex, arriving precisely in the moment the cortex is primed. This is the three-way handshake. This is the choreography of the filing itself. It is worth finding an image that holds this because the image is what will carry it with you. Think of the slow oscillation as a tide, a big, slow ocean tide, rising and falling across the cortex in the dark. Most of the time the water is out. The shore is quiet. But when the tide comes in, the upstate, the crest of the slow wave, the water covers the shore and makes it available. Then the spindle arrives like a wave riding the high tide, concentrating the energy in one place, stirring the water in one particular cove. And inside that wave, at its peak, the ripple delivers its message, a sharp, fast pulse, carrying the day's experiences like a note in a bottle, arriving precisely when and where the shore is ready to receive it. Miss the tide and the ripple delivers its message to dry sand. Hit the window exactly and the message lands where it was always meant to go. Scientists studying this nesting have found that it is not approximate. It is not as though the ripples roughly coincide with the slow oscillations, and that's close enough. The timing is specific and consistent. The ripple consistently fires in the upstate. The spindle consistently couples to the same upstate. The three rhythms lock together in a way that looks, in the data, less like an accident of overlapping biological timers and more like a system that evolved to work this way. This is the spine of the whole process. Not stages of sleep as a list, not the familiar cascade of REM and non-REM cycling through the night as a sequence to memorize, but this, a precise, recurring, three-layered electrical event happening thousands of times across a night of good deep sleep, each iteration carrying a small packet of experience from the fast door to the slow, the hippocampus speaking to the cortex in the only language the filing system understands, the language of perfectly timed waves. Now let us go a little deeper into the middle doll, the spindle, because the spindle does something more than timing. When researchers began comparing how many sleep spindles a person generated during a night of sleep, spindle density, as it's called, with how much they remembered the next day, a consistent pattern emerged. More spindles after learning predicted better recall. Not perfectly, not in every study, not in every person. But the relationship was there, and it was there reliably enough across enough labs and enough different memory tasks that it became one of the more robust correlations in the field. Studies from researchers including Sharbus and colleagues, and separately from Fogel and Smith, found this relationship not just for overnight memory gains, but for something even more striking. Spindle density correlates with general cognitive ability, with what in blunt terms we sometimes call IQ. More spindles, on average, in people who score higher on measures of intelligence and working memory. Now, here it is essential to be careful, because this is one of those findings that is true and important and can be misread in ways that lead somewhere the evidence does not actually go. The relationship is correlational. More spindles and higher cognitive scores are found together. This does not mean that generating more spindles makes you smarter, any more than the fact that taller people tend to weigh more means that gaining weight will make you taller. The correlation tells you the two things are related, that spindles are not just noise but are tracking something real about the brain's capacity and performance, without telling you the direction of causation or whether you could intervene on spindles and move the needle on cognition. What it does tell you, honestly and with good evidence, is that the spindle is not a trivial side effect of deep sleep. It is doing something important, something that matters enough that it shows up in the signature of high-functioning cognitive systems. What specifically might it be doing? The leading hypothesis has to do with calcium. When a sleep spindle fires, when that burst of 11 to 15 per second activity surges through a cortical neuron, it is accompanied by a transient influx of calcium ions into the cell. Calcium, in neurons, is a signal. It is one of the molecular messengers that activates the internal machinery of synaptic change. The protein synthesis, the receptor insertion, the structural remodeling at the synapse that physically cements a connection that was previously only temporary. This is what long-term potentiation looks like at the cellular level, not a metaphor of strength, actual molecular machinery, building actual new proteins, physically stabilizing the synaptic trace. The spindle in this account is not merely a timing signal, it is a key. Each burst of spindle activity opens what researchers sometimes call a plasticity window, a brief period during which the calcium influx triggers the cascade of molecular events that solidifies the memory trace. The hippocampal replay arrives via the sharp wave ripple at precisely the moment the cortical neuron is flooded with calcium and its plasticity machinery is activated. The memory is not just delivered, it arrives in the moment the door is open and the cement is wet. Let us explore a story about this. Imagine a restorer working on an old painting. The painting has been photographed, a quick digital record made, light and portable and easily retrieved. But the photograph is not the painting. It can be corrupted, it can be lost. If the server fails, it holds no texture and no depth. The real painting has to be restored onto a surface that will hold it for decades. Canvas, primer, paint. Now imagine the restorer can only work during a specific kind of light, a particular quality of afternoon sun through a north-facing window when the temperature and humidity are exactly right for the varnish to bond. Outside that window, the varnish won't cure. The painting won't hold. You can try all you like, but the conditions aren't there. The plasticity window opened by the calcium influx of the sleep spindle is that light. The sharp wave ripple is the restorer arriving with the original photograph. The slow oscillation is the cycle of light and dark that guarantees the window will come again and again across the night. Not just once, but reliably, each time the upstate crests and the spindle and the ripple are ready to nest inside it. Thousands of restoration windows in a single night, thousands of small deliveries, each one arriving at precisely the right moment, each one adding another layer to the slowly building archive of what you know and who you are. This is not a metaphor invented to make the science prettier. It is the mechanism described in terms that try to be true to what the data actually shows. The calcium influx is real. The spindle's timing relative to the slow oscillation is real. The correlation between spindle density and memory retention is real. The nesting of ripple inside spindle inside slow oscillation is real and measured with specificity in dozens of studies. What we are describing is not an interpretation of the science. It is the science given an image that can hold it through the night. And it means something for you, lying here right now, as your own brain begins its slow descent into the first long trough of deep sleep. The slow oscillations are gathering in the prefrontal cortex. If this is early in the night, if the hours ahead of you are good and uninterrupted, the first long stretch of deep, slow-wave sleep is about to begin, and with it, the first session of the night's most intensive filing work. The thalamic reticular nucleus is already beginning to organize itself for the rhythmic loop that will produce the spindles. The hippocampus, holding today's incomplete traces, is preparing its sharp wave ripples. In a little while, not yet, but soon, the first slow oscillation will crest into its upstate, the first spindle will rise within it, and the first sharp wave ripple will fire inside the spindle, and somewhere in the cortex, a neuron that is flooded with calcium will receive a fragment of today as though it were arriving for the first time, and the cement will begin to set. You will not feel it. There is nothing to feel. This is one of the most extraordinary things about the whole process. It is entirely unconscious, entirely invisible, conducted without any participation or effort or awareness on your part. The archivist works only in the dark, only in the quiet, only when you have finally set down the day and stopped interfering. Your waking mind, with all its reaching and reviewing and rerunning of the day in anxious replay, that is not what does this. It is, in fact, something like the opposite of that. The waking mind makes the memories, the sleeping brain files them, and the filing requires you to do nothing at all except let the night be long and still. Rest pause. Let this one breathe. Take a slow breath in. Feel the chest lift slightly, just slightly, and then let it go all the way down until the last of it has left and there is only quiet. Notice how the body has shifted into the bed since we began. Notice the weight of your arms, the particular warmth of the places where the blanket touches skin. You have been receiving something. Words, ideas, images, the small electrical weather of understanding. And now you do not need to hold any of it consciously. Your hippocampus has it. The day has it. The night will do what it always does with what the day handed it. There is nothing to figure out. The three rhythms are not yours to manage. The nesting of wave inside wave inside wave will happen or it will not, according to the depth and length and quality of the sleep your body finds tonight. And the very best thing you can do for all of it is to let yourself go entirely, here, now, without resistance. The spindles arrive only when the cortex has gone still enough for slow oscillations to form. The slow oscillations form only in the genuine quiet of deep sleep. And deep sleep comes only when the part of you that monitors and reviews and manages finally, fully releases. So let it release. Let the review stop. Let the inbox close. Let whatever the day left unresolved remain unresolved for now, because the night is not where resolutions are formed. It is where they are quietly prepared, laid down in the architecture of tomorrow's understanding, so that when the morning comes you may find that something has shifted in you, some piece of the world sitting differently than it did the night before, the edges of a problem softer, the shape of a difficulty cleaner, without knowing quite when or how it changed. The three rhythms will take care of it. The slow oscillation will set the tide. The spindle will open the window and let the calcium in. The sharp wave ripple will carry the day's keepers across. And you need only be here, warm and heavy and still and breathing. That is the whole of it. That is all the work that remains for you tonight. When you are ready, speak in no hurry at all, whenever the breath wants to carry you forward, we will continue. Into the different rooms of the night, where different kinds of memory are handled by different kinds of sleep. into the first half of the night where the facts are filed, into the later hours where something quieter and stranger happens, where the painful things are carefully processed and the charge is slowly drained from the memories that arrived with too much feeling attached, and where the brain does something that looks in the data almost exactly like dreaming itself toward wisdom, but that is ahead of us in its own good time. For now, only this: the body sinking, the waves gathering, the archivist already at the desk, already working, already carrying today toward tomorrow with a patience and a care that asks nothing in return and never once stops to rest. So let us go there now, into the first half of the night where the work of facts begins. There is a division of labor in your sleeping hours that most people never think about, because sleep, from the outside, looks like one undivided thing. The lights go out, you are gone. Hours later, you return. But the night is not a single room. It is a series of rooms, each arranged for a different kind of work, each populated by a different quality of sleep, and the brain moves through them in an order that is not random, not accidental, but carefully choreographed by something that has been solving this problem for a very long time. The first rooms you enter are the deep ones, and in the deep rooms the facts are filed. This is slow-wave sleep. Researchers call it SWS, or deep NREM, or stage N3, and all three names point to the same territory: the profoundest, most anchored, most physiologically heavy sleep you will experience in the night. It is the sleep that makes you feel the next morning as though you had not moved. The sleep during which you are most difficult to wake. The sleep during which a child might be lifted from the car seat and carried to bed without stirring at all, without any trace of it remaining in the morning. And it is also the sleep during which your brain is doing the most deliberate, most structured work it will do all night. A pair of researchers named Werner Plihal and Jan Born, working in Germany in 1997, designed an experiment that illustrates this beautifully. They wanted to know not just that sleep helps memory, but which part of sleep helps which kind of memory. So they split people into groups. Some learned material and then slept only the first half of the night, going to bed late and waking in the small hours. Others learned material and slept only the second half, going to sleep in the early morning and waking when the day had already begun. And because of the way the night naturally organizes itself, the first group got mostly deep, slow-wave sleep, and the second group got mostly REM sleep, the lighter, more vivid, more dream-saturated sleep that concentrates in the later hours before dawn. What they found has never quite left the field. For declarative memory, for the kind of memory that holds facts and word pairs and the kind of information you might encounter in a classroom or a book, the first half sleepers did significantly better. The deep sleep of the early night was doing the heavy lifting for knowledge. The late sleepers, swimming in REM, remembered less of the factual material. For other kinds of memory, the picture reversed, and we will get to that. But for now, for the question of how facts become permanent, Plihal and Born had isolated something important. The archivist that files your knowledge works the early shift. It works in the deep, slow, heavy hours before midnight has fully passed. And understanding why requires going back to those three rhythms we met a little while ago and seeing them from the inside, from the perspective of what they actually accomplish for the material trying to move from the hippocampus to the cortex. Remember the two stores, the hippocampus, fast and fragile and small, holding today's new information in a state of temporary suspension, still needing to be confirmed and relocated. The neocortex, vast and patient and slow to change, where knowledge will eventually live permanently, woven into the wider fabric of everything you already know. The problem is that the neocortex does not learn quickly. It cannot be written to the way you might save a file to a hard drive in one swift action. It changes gradually through a process of slow synaptic adjustment that requires repeated exposure, repeated reactivation, something hitting the same networks again and again until the connections strengthen and the pattern settles in. That is why you cannot, as a child, read a word once and know it forever. The cortex needs repetition. It needs to encounter the same thing from different angles, in different contexts, till the shape of it becomes part of the permanent landscape. And this is precisely what deep sleep provides. Each time the hippocampus replays a memory, each time the sharp wave ripple carries the compressed rerun of today's experience, it nudges the corresponding cortical networks, not enough to change them permanently on the first pass, but enough to leave a small trace, a slight strengthening of a connection that was not quite there before. And then the ripple comes again, riding the next spindle during the next up state of the slow oscillation. And again, through the hours of the early night, the same memories are represented dozens or hundreds of times to the cortex. And with each presentation, the cortical trace grows slightly stronger, slightly more stable, slightly more capable of existing on its own, without the hippocampus to hold it up. It is the way that water carves stone, not in one great act, but through return after patient return, each pass leaving the groove a little deeper than before. And somewhere in that gradual deepening, the memory crosses a threshold. The cortex, which initially could not have retrieved it without prompting from the hippocampus, develops enough of its own representation that it can begin to hold the knowledge independently. The fact has been filed, the archivist has done its work. But here is the part of this that stops me every time I think about it carefully. The archivist can be guided, it can be steered. And the evidence for this came from a study so elegant in its design, so simple in its apparatus, that it almost seems like it shouldn't have worked. And yet it did, cleanly and repeatedly. And it changed the way researchers think about what memory consolidation is. Björn Rasch and Jan Born in 2007 published a study in the journal Science. And the central tool of that study was a smell, rose. The warm, particular, slightly sweet scent of rose. Here is what they did. People came into the laboratory and learned the locations of pairs of cards on a grid, the kind of memory game children play, where you flip cards looking for matches and try to hold in mind where you have already seen each one. While they were learning, a subtle rose odor was diffused into the room. The scent became, without the participants being consciously aware of it, associated with the material being studied. It became, in the language of conditioning, a cue. Then the participants slept. And while they were in slow-wave sleep, some of them were gently, quietly, undetectably re-exposed to the rose scent. Not enough to wake them. Not enough to disturb the depth of the sleep. Just a breath of rose floating through the room, while the slow oscillations moved their long tides through the brain. The next morning, the people who had received the rose scent during their slow-wave sleep remembered the card locations significantly better than those who had not. The cue had reached down into the sleeping brain and nudged it toward the associated material. Had said, in the only language available, this is the one worth keeping. This is the one to run again. And here is the part that makes this more than a curiosity. When the same scent was delivered during REM sleep, there was no benefit. When it was delivered during waking rest, there was no benefit. It only worked during slow-wave sleep. During the precise phase when the hippocampus and cortex are in active dialogue, when the replay is running, when the transfer is already in progress. The smell did not create a memory. It did not install anything new. It simply tipped the scale during the consolidation process, redirecting the brain's overnight triage toward the cued material, strengthening what was already there, waiting to be decided upon. This is the true kernel inside the old fantasy of sleep learning. The fantasy says, play a tape of Spanish vocabulary through a speaker while you sleep, and you will wake knowing something you did not know when you closed your eyes. That version is false. The brain cannot take in brand new, complex information during sleep and convert it into lasting knowledge. That is not what sleep is for, and the studies have been clear on this point for decades. The encoding of new material, the initial catching of a new experience, that work requires a waking brain. But Rasch and Bourne showed something real and genuinely surprising nested inside the false version. You cannot learn while you sleep, but you can steer what you consolidate. You can cue the sleeping brain toward the things you most want it to keep, and it will weight them preferentially in its overnight filing. The process that people have always wanted sleep to do, it turns out it does do, only in a more limited and more specific way than the dream version, not instruction, curation. Let us sit with that for a moment. The idea that your sleeping brain is not a passive recipient of whatever the day has left behind, but an active sorting system that can be influenced by something as quiet as a scent drifting through a room. And if a smell can do it, what else might? Researchers have explored this question with tools that move from the elegant to the genuinely remarkable. Jan Bourne's group, working with Jan Matthias Ngo and colleagues, published findings in 2013 in the journal Neuron describing what they called closed-loop acoustic stimulation. The idea was this: if the upstate of the slow oscillation is the window during which memory transfer happens, what would occur if you gently amplified the slow oscillations themselves? They did it with sound, soft clicks timed precisely to arrive during the upstate of each slow oscillation, detected in real time by electrodes on the scalp and delivered through small speakers. The brain heard a click timed to its own rhythm, and the rhythm strengthened. The upstate grew a little longer, a little more pronounced, and with it, memory for the material learned before sleep improved. Earlier work by Lisa Marshall and colleagues, published in Nature in 2006, had shown something similar with a different tool. Transcranial direct current stimulation, which researchers refer to as TDCS, involves passing a very gentle electrical current through the skull while a person sleeps. Marshall's group applied oscillating current at 0.75 Hz, the frequency of the brain's own slow oscillations during early night NREM sleep. It was just enough to nudge the brain's rhythms in the direction they were already heading, and the result was an increase in slow oscillation power, an increase in sleep spindle activity, and a significant improvement in next-day recall of declarative material compared to a placebo condition. Both of these findings are research findings. They are not techniques to try at home. The precision required to time the cues, to calibrate the current, to avoid disrupting rather than enhancing the very rhythms you are trying to support, that precision lives in a laboratory with EEG equipment and careful controls. What they demonstrate is a principle, not a recipe. That the brain's memory filing system is not a sealed room operating in perfect isolation from the world. It is responsive. It can be influenced, and those influences can change what you remember. The implication for everyone who has ever lain awake wishing their studying would stick, who has ever put down a book and wondered whether any of it would survive the night, is not a product to buy. It is a principle to understand. The consolidation process is real, it is active, it is tunable in the laboratory, and understanding that it exists, that it is doing something specific and valuable during those early hours of heavy sleep, is itself a reason to protect them. Just take a slow breath here and feel, if you are willing, the particular quality of the darkness around you now. The early night is doing its work wherever you are in your own cycle. The slow waves are moving, and somewhere in the rhythm of them, if today held anything worth keeping, it is being considered. Run again, quietly carried forward. When you are ready, we will continue. Because we have talked so far about facts, about the kind of memory that holds information, knowledge, the sort of thing that can be tested and recalled in explicit language. But there is a second room in the night's architecture, and it handles something altogether different. The later hours. The place where REM sleep concentrates, where the dreams grow longer, and stranger, where the brain enters a state so different from deep, slow-wave sleep that some researchers have described it as closer to a second waking than to rest. And this is where the emotional memories come. To understand what happens to emotional memory during sleep, you need to hold one fact in your mind, and it is a fact that still surprises me no matter how many times I return to it. Noradrenaline, which you may also hear called norepinephrine, is one of the brain's primary stress and arousal chemicals. It is the neurochemical signature of threat, of urgency, of the heightened, vigilant state that comes when something important or frightening is happening. It is what makes the heart quicken and the attention narrow. And it is, among other things, the chemical that encodes the emotional intensity of an experience, that wraps the feeling around the memory and makes it feel significant, makes it persist, makes it vivid in a way that ordinary neutral events never achieve. During REM sleep, noradrenaline is at the lowest level it will reach across the entire 24-hour cycle, not diminished, not reduced to a modest baseline. At its floor. The brain in REM sleep is a brain that has, for the duration of that phase, essentially switched off its primary stress chemistry. Matthew Walker, a neuroscientist at the University of California, Berkeley, and his colleague Els van der Helm articulated what this might mean for emotional memory in a 2009 paper, and the phrase they used for it has stayed in the field as a kind of shorthand: sleep to forget, sleep to remember. The idea is this: when an emotional memory, something charged with fear or sadness or grief or shame, comes back to be processed during REM sleep, it comes back into a brain that has removed the stress chemical from the room. The memory is replayed, the events are re-encountered, the faces, the words, the sequence of what happened, all of that information is present and active. But the neurochemical context in which it is being re-experienced is profoundly different from the context in which it was first lived. The memory arrives at its REM reactivation in a brain from which the sting has been temporarily withdrawn. And the theory, supported by the evidence, is that this is not accidental. This is the mechanism by which painful memories are processed into something livable. The brain is not erasing the memory. It is not pretending the difficult thing did not happen. It is keeping the information, the who and the what and the when, while slowly, over repeated REM cycles, draining the visceral charge. The raw, gasping intensity of the feeling is what fades. The understanding remains. Walker and van der Helm and their colleagues asked people to look at emotionally evocative images, then either sleep or stay awake for 12 hours, then look at the same images again in a brain scanner. The people who had slept showed measurably reduced activity in the amygdala, the brain's emotional alarm center, when they viewed the images the second time. The people who had stayed awake showed no such reduction. The emotional reactivity was still at its original intensity, the signal still firing as though the threat were fresh. Sleep had not made them forget the images. It had changed how they felt about them. This is why, in ordinary human experience, time plus sleep is the thing that heals the emotional wounds that time alone does not. Why a loss that was unbearable in the first weeks becomes, months later, bearable, not because you have forgotten the person, but because the raw, splitting quality of the pain has been slowly processed across dozens or hundreds of REM cycles into something you can carry. The information stayed. The anguish slowly gave way to something you could hold. And when people tell each other to sleep on it, when a grandmother says there is no problem that looks the same after a good night's sleep, they are not offering mere comfort. They are describing, without knowing the neuroscience, the precise mechanism that Walker and van der Helm documented. The the world looks different in the morning, partly because the brain's chemistry has shifted, but also partly because something in the processing of the night before has, however subtly, begun to change the weight of what you are carrying. There is another thread here, one that requires care in how it is held, because the evidence for it sits in a complicated place, part established mechanism, part active debate. And that thread connects this noradrenaline story to what happens when the REM processing system fails. Post-traumatic stress disorder involves, among its many features, memories that have not been processed, memories that remain at their original emotional intensity, that intrude without warning, that replay with the full charge intact, as though no time had passed, as though the brain had never gotten the chance to drain the feeling from the facts. The nightmares of trauma are, in this light, a system that is trying to do its job and cannot quite complete it, re-encountering the memory again and again without the chemical conditions that would allow the processing to finish. A drug called prazosin works by blocking noradrenaline receptors, and clinical observations have found that prazosin can reduce trauma nightmares in some people with PTSD, which is exactly the kind of finding you would expect if the noradrenaline theory of REM processing were correct. If the system is failing partly because noradrenaline is not fully suppressed during REM, as some research suggests may be the case in PTSD, then a drug that blocks noradrenaline's effects might restore some of what the undisturbed system provides. The mechanism is coherent, the theory is consistent with the sleep neuroscience, and yet the clinical trial results for prazosin in PTSD have been, in the honest telling, mixed. Some trials show clear benefit, others show less than hoped for. The relationship between the neuroscience of REM processing and the clinical reality of trauma treatment is not a clean, settled story. It is an active area of research with real promise and real uncertainty, and it deserves to be held that way as a direction that the evidence points, not as a conclusion that has been reached. What the REM research does establish clearly and robustly is the principle that sleep in general and REM sleep in particular is not neutral in its relationship to how we carry what happens to us, that the chemistry of the dreaming brain is specifically configured to do something that the waking brain cannot replicate, that the emotional weight of experience is, in the healthy sleeping brain, actively metabolized across the night. But REM sleep does not only process emotional memory, it does something else as well, something that belongs in a different category, and that has produced some of the most striking experimental findings in this entire area of research. It extracts meaning. There is a study from 2004 published in Nature by Ulrich Wagner and Jan Born and their colleagues using a task called the number reduction task. Participants were given long strings of numbers and taught a set of rules for transforming them into a response sequence. They practiced and practiced, learning the procedure step by step. What they were not told was that the task contained a hidden rule, a shortcut, a pattern embedded in the sequences that made the whole thing much simpler if you could only see it. And most people, working through the task consciously, applying the explicit rules they had been taught, did not see it. They completed the task, but they completed it the long way. After training, some participants slept for a night and some stayed awake. The next day, the people who had slept were more than twice as likely to have discovered the hidden rule. Not because they had thought about it consciously, not because they had sat and deliberately searched for the pattern, but because the sleeping brain, moving through its cycles, had done something with the material that the waking brain, grinding through it procedurally, had not. It had found the shape beneath the surface. It had abstracted upward from the specific instances of the task to the general structure underneath them. This is what researchers mean when they talk about REM sleep favoring gist over detail, abstraction over specifics. The waking brain, encoding experience, tends to capture the particulars, this word, this face, this sequence of steps. The sleeping brain, especially during REM, seems to be asking a different question. Not what happened, but what does it mean? Not the specific instance, but the pattern it belongs to. Not the individual fact, but the category it implies. The dreaming brain in this reading is doing something that resembles wisdom more than memory. It is looking for what generalizes. And the finding from Wagner and Bourne suggests that the insight people sometimes wake with, the sense that a problem you took to bed looks different, cleaner, more solvable in the morning, is not simply rest having restored your capacity to think. It is the sleeping brain having continued to work on the problem in a different register, at a level of abstraction that waking cognition does not naturally access. There is a long and possibly unresolvable question about how much of deliberate creative insight, how much of the breakthrough that arrives after sleeping on a problem is genuinely produced by REM's processing, and how much is simply the ordinary benefit of returning to something with a rested, less tired mind. The science does not yet have a clean answer, but the number reduction task with its doubled rate of hidden rule discovery after sleep is evidence that something more than mere rest is happening, that the night is not passive, that the brain working in its absence is working differently, and that difference produces real gains in understanding that the rested but waking brain alone does not achieve as readily. And so when a mathematician or a poet or an engineer says that the solution came to them in a dream, or that they woke knowing how to do something they had not known the night before, they are pointing, however imprecisely, at a real phenomenon, not magic, not the unconscious in any mystical sense, but the brain doing its abstracting work, finding the shape of things while the analytical, detail-oriented, sequential, waking mind is, for once, not running the show. Let us pause here, gently. Take a slow, unhurried breath. Let it arrive without effort. Let the body receive it. Notice, if you like, that you are already somewhere in the night, that some part of the process we have been describing is right now either already, underway, or approaching. That the rooms ahead of you in your own sleep cycle are waiting. The early rooms with their slow, deep work of filing facts. The later rooms, saturated with REM, where the feeling is metabolized and the gist is found. You do not need to direct any of it. You do not need to think about it or hold any particular thing in mind. The brain knows what to do. When you are ready, in your own time, we will continue into the final things, into what happens when the night is cut short, into the stakes of the thing we so often give away without knowing what we are giving, into the long, slow damage of a filing system that never ran, and the remarkable findings about what accumulates in its place. But for now, only this: the rose scent drifting through the slow wave room. The noradrenaline switched off in the later hours. The sleeping brain quietly finding the shape of what the waking brain could not quite see. The night is doing its work, and you are safely inside it, and there is nothing left for you to do but let it. There is a study from 1924 that has always stayed with me, perhaps because it is so simple that it should not have needed doing, and yet it changed how we understand forgetting in a way that still holds a century later. Two psychologists, John Jenkins and Carl Dallenbach, asked their subjects to memorize a list of nonsense syllables, sounds with no meaning, strings of letters that the brain cannot cheat on by connecting them to something already known. And then they divided the subjects into two groups. One group went to sleep shortly after learning. The other stayed awake for the same number of hours before being tested. The question Jenkins and Dallenbach were asking was a simple one. Is forgetting caused by time passing, or is it caused by something that happens during the time? The answer, when it came back from the data, was startling. The people who slept forgot far less. Not slightly less, substantially, unmistakably less. The people who had spent those same hours awake going about ordinary life, had lost far more of what they had learned. What this told them, and what it has been telling researchers ever since, is that forgetting is not simply the passage of time doing its quiet erosion. Forgetting is driven in large part by interference, by the new experiences and inputs and stimuli of waking life crowding in and bumping the fragile new traces out of their holding place. The sleeping brain, protected from that tide of new information, holds what it has. The waking brain keeps receiving, and what was just arriving gets pushed aside. This reframing is worth sitting with for a moment. We tend to think of forgetting as something passive. The memory fades like a photograph left in the sun. But Jenkins and Dallenbach were pointing at something more active than that. Waking life erases. The ordinary business of being conscious and present and responsive to the world is itself a kind of interference, a noise that drowns out what was just laid down. Sleep is not simply a pause in that process, it is a shelter from it. Sleep after learning is not a luxury. It is the window during which what was learned has a chance to be moved out of the fragile, interference-prone holding space and into something more durable. Miss the window and you have not just lost a few hours of consolidation. You have let the world's ordinary noise do its work on something that had not yet had time to be protected. And there is something else the sleeping brain does with those hours, something more deliberate than merely sheltering the fragile new traces. It sorts. Researchers, including Ines Wilhelm and her colleagues, published findings in 2011 showing that the brain does not treat all new information equally during the night's consolidation work. Sleep preferentially strengthens memories that the brain has somehow tagged as important, material that you were told you would be tested on later, experiences that carried emotional weight, information that was attached to a reward. These get the best seats in the overnight filing process. The incidental, unimportant, unremarkable details of the day are allowed to drift. There is an overnight triage happening. The brain, in those quiet hours, is not simply consolidating everything it received. It is making decisions. This matters, this can go, this is the thing that needs to survive until morning. And it is doing this in ways that align with what the waking mind had flagged as worth caring about, without the waking mind being present to direct it. Think about what this means for the way most of us study. The hours spent going over something and the hours spent sleeping after are not in competition. They are in partnership. The studying tells the brain what to care about. The sleeping is when the caring is translated into lasting structure. And the partnership extends to something even shorter than a full night. In 2008, a team led by Olaf Lahl published findings that have become one of the more quietly surprising results in the sleep and memory literature. They found that a nap, even a very short one, even one lasting only 6 minutes, showed measurable benefits for declarative memory. 6 minutes, less time than it takes to make a cup of tea. The effect was small, as you would expect from something so brief, but it was there. Something in even the earliest minutes of sleep begins the protection process. A nap of 60 to 90 minutes, long enough to contain both some slow-wave sleep and some REM, can produce consolidation benefits that in some tasks approach what a full night achieves. The brain does not seem to require the full 8 hours of filing time to accomplish something meaningful. What it requires is the opportunity to enter the right states, even briefly, and begin. This does not mean that brief naps replace the full night's work. They do not. But it means the system is eager, primed, ready. Given even a small window, it begins. That readiness, that eagerness to file and protect and sort, is the brain taking the task seriously in a way the waking mind rarely appreciates. Let us pause here, just for a breath. Take it slowly. Let the air arrive without effort. We will move now into something that many people have experienced and not known what to name. The thing that happens overnight with a skill, with something practiced, with the body's memory of a movement or a sequence. There is a particular experiment that researchers in Matthew Walker's group ran in 2002, published in the journal Neuron, and it has stayed in the literature because what it found is almost difficult to believe until you have sat with it for a while. They trained people on a finger-tapping sequence, a specific pattern like learning a short melody on a piano keyboard. The subjects practiced until they had the sequence, then they were tested the next morning. And the finding was this: the people who had slept between practice and testing were roughly 20% faster than they had been at the end of practice. Not 20% faster than the people who hadn't slept, 20% faster than themselves. Overnight, having done nothing, having not touched a keyboard, having not practiced a single repetition, they had improved. The people who waited the same amount of time but stayed awake did not show this gain. The improvement was specific to sleep. It was not time that produced it. It was not rest in some general sense. It was sleep, and it correlated specifically with the density of sleep spindles in stage 2 NREM, that middle, lighter layer of slow-wave sleep where the thalamic reticular nucleus generates its characteristic bursts of electrical activity. This phenomenon is called the offline gain. The skill was being worked on in the absence of practice, in the absence of the practitioner's conscious involvement or effort. The brain was using the sleeping hours to consolidate the motor sequence, to refine its representation in the motor cortex, to make it faster and smoother and more reliably available the next morning. Musicians know something of this in an intuitive way. There is a tradition in certain teaching lineages of advising students to practice something difficult and then sleep, and not to over-practice, not to grind the same passage past the point of useful fatigue. The wisdom in that advice is older than the neuroscience, but the neuroscience has now given it its explanation. The practice loads the material, the sleep does the refining. It is strange and beautiful, this offline economy. The brain has arranged to be most productive at the task of skill building during the hours when you are not doing the task at all. There is something in that which feels like a reminder that effort and result are not always as directly linked as we tend to assume. Some of the most important work happens in the spaces between the striving. Now, let us move into what happens when those spaces are taken away. This is where the conversation changes register, because everything we have been describing, the replay, the sorting, the filing, the 3-rhythm handshake, the overnight therapy, the offline gain, all of it depends on sleep actually happening. And there are things we do regularly without quite knowing the cost that prevent it. There is a finding from Seung-Shik Yu and colleagues in Walker's group, published in Nature Neuroscience in 2007, that tends to stop people when they hear it. They asked subjects to stay awake for one full night, and then the next day they attempted to learn new material while lying in a brain scanner. What the scanner showed was that the hippocampus, that fast-learning inbox where new memories are first caught, had essentially gone quiet. Its encoding activity compared to people who had slept normally had dropped by roughly 40%. 40%. Not a modest decline, not a slight dulling. The brain's ability to receive and hold new information had been cut nearly in half by a single sleepless night, before the person had even opened a book, before they had tried to study anything at all. And this is perhaps the most counterintuitive finding in this entire field of research. Sleep is not only needed after learning to consolidate what you have taken in. It is needed before learning to prepare the system to take anything in at all. The hippocampus needs to have run its filing cycle to clear space for new arrivals. Without the overnight transfer, without the consolidation pass, the inbox is full. New material has nowhere to land. The person who stays up all night to cram before an exam is, in the most literal neurological sense, trying to write on a whiteboard that has not been erased. The words go down, but imperfectly, incompletely, onto a surface that is already cluttered with everything that did not get filed the night before. And it gets harder still. The consolidation window matters. A memory that forms in the hours before sleep needs that night's sleep to complete the transfer. If the sleep is missed, the window closes. Research has found that the deficit is not fully rescued by later recovery sleep. You can catch up on rest in the sense of feeling less tired, but the memory that needed that specific night's consolidation pass cannot be retrieved by sleeping the following night. The moment has passed. The file never moved from the inbox to the archive, and by the time the next filing cycle runs, that particular trace has degraded past the point of clear retrieval. There is something quietly sobering about this. We tend to think of memory loss as something that happens gradually, over years, through age or illness. But the research on sleep deprivation suggests that significant memory degradation can happen in a single night. The contents of a day's experience, imperfectly held in a hippocampus that was already tired, exposed to a full waking day's worth of interference without the protection of sleep, can simply not make it through to the morning in any usable form. And there is something else that sleep deprivation does to memory that is perhaps even more unsettling than the forgetting. It makes the memories that do survive less trustworthy. Research led by Stephen Frender and colleagues, published in 2014, found that sleep-deprived people are significantly more prone to false memories. They misremember events that did not happen. They accept misinformation more readily. They fill gaps in their recall with plausible-seeming details that were never there. The tired brain, trying to reconstruct an experience from fragments, is less careful about the reconstruction. It substitutes, it infers, it confabulates. And the person doing this has no way of knowing from the inside that their memory is unreliable. The false memory feels like a real one. This has implications that reach well beyond the individual trying to remember where they left their keys. It touches questions of eyewitness reliability, of institutional decision-making, of any situation in which accurate recall matters, and people have been asked to perform on insufficient sleep. When the filing system runs poorly, what gets stored is not just less, it is also less accurate. And then there is the question of what accumulates while the system is not running. Take a slow, easy breath. Let it come and go without effort. The glymphatic system is the brain's own waste clearance pathway. The word comes from combining glial cells, the brain's support cells, with lymphatic, the body's more familiar drainage network. It works differently from the lymphatic system in the rest of the body, but it serves a similar function. It flushes the brain's interstitial space, the microscopic gaps between cells, clearing out the metabolic byproducts that accumulate during the work of being alive and awake. And it works almost entirely while you sleep. Research from Mike and Nedergaard's group, published in Science in 2013 by Lulu Ji and colleagues, found something remarkable when they looked at this system in mice during sleep. The spaces between brain cells expanded by roughly 60% during sleep, allowing cerebrospinal fluid to flow through much more freely and flush the tissue with far greater efficiency. The clearance of metabolic waste, including beta amyloid, the protein that aggregates into the plaques associated with Alzheimer's disease, roughly doubled during sleep compared to the waking state. 60% expansion. Double the clearance rate. The sleeping brain is not simply less busy, it is doing something the waking brain cannot do, because the waking brain cells are, in their active state, too tightly packed to allow the flow. Beta amyloid is a protein that forms naturally in the brain as a byproduct of normal neural activity. During waking hours, some accumulates. During sleep, the glymphatic system flushes it out. The balance in a healthy brain that is sleeping enough is maintained. The protein is produced, and it is cleared, and it does not accumulate. When sleep is regularly cut short, the balance tips. The production continues as it always does during waking activity. The clearance, which depends on the glymphatic system, is reduced. The protein begins to build up. The connection between sleep deprivation and the risk of Alzheimer's disease is not simple, and it is not fully settled. The relationship appears to be bidirectional, meaning that the disease process, once underway, also disrupts sleep, creating a difficult cycle where each makes the other worse. And most of the mechanistic research on the glymphatic system has been conducted in rodents, so the human version of the story is inferred rather than directly observed with the same precision. But the inference is not wild. In 2018, a study by Ehsan Shokri Kajori and colleagues, published in the Proceedings of the National Academy of Sciences, used PET imaging to measure beta amyloid levels in the human brain after a single night of sleep deprivation compared to a night of normal sleep. After the sleepless night, amyloid levels in the hippocampus and the thalamus were measurably elevated. One night, not a decade of short sleep. One night was enough to produce a detectable increase in the protein the brain works to clear each time you close your eyes. What researchers are careful to say is that sleep deprivation is a recognized risk factor for dementia, not a proven cause. The brain is complex, and Alzheimer's disease is influenced by many things, but the mechanistic story is coherent, and it is concerning, and it is worth knowing. The image it gives is a striking one. Every night of sleep is, among all the other things it is, a cleaning, a power wash of the brain's interstitial space. The gaps between cells opening up, the fluid moving through, the protein that has been building all day being carried away. The night worker with the hose and the drains. Skip the shift and the protein sits there a little longer. Skip enough shifts, and it begins to accumulate in ways that matter. We started this journey with the image of the brain as a night shift archivist, filing memories from the fragile inbox to the durable archive. And that image has held up through everything we have described, but there is now this other layer to it, this other work, running in parallel with the filing, the archiving and the cleaning happening at the same time in the same sleeping hours, one as essential as the other. A word gently about two things that float around this topic and deserve to be addressed directly. The first is the idea that you can learn while you sleep, that playing recordings of a language or vocabulary lists or anything you want to absorb through speakers while you are unconscious will allow you to encode new information without any effort at all. This is an appealing idea. It shows up repeatedly in popular culture and has driven the sale of many products over many decades. The strong version of this idea is not supported by the evidence. You cannot encode brand new complex information during sleep. The sleeping brain is deeply occupied. It is busy with exactly the work we have been describing. It is not available to receive fresh material from the outside world and build new memory traces for it the way the waking brain does. But there is a real and subtle truth hiding inside the myth, and it comes directly from the targeted memory reactivation research. What the sleeping brain can do is strengthen material it has already learned while awake, re-expose it to a cue that was paired with that learning, and the sleeping brain will prioritize the associated memory in its consolidation work. The rose scent that appeared in the Rachenborn experiment did not teach the brain new geography. It told the brain which geography already learned awake to file with extra care, so you cannot learn in your sleep, but you can, in a careful, research-informed way, nudge the sleeping brain toward the things you most want it to retain. The learning has to happen first, while you are awake and present. The sleeping brain's extraordinary contribution is what it does with the learning afterward. The second thing worth addressing is the common assumption that the sleeping brain is simply at rest, that it has powered down the way a laptop screen goes dark, that the business of thought and processing is paused until morning. We have spent this entire journey disassembling that idea piece by piece. But it is worth saying plainly here, near the end. Some regions of the brain during REM sleep are more metabolically active than they are during waking. The hippocampus is firing its place cells in rapid, compressed sequences. The thalamus is generating its coordinating spindles. The cortex is rolling through its slow oscillations, setting the rhythm for everything. The glymphatic system is running its fluids through the expanded interstitial space. The amygdala is reprocessing emotional experiences with the noradrenaline switched low. The brain is working hard, not in the same way it works during the day, not toward the same goals, but the activity is real and it is purposeful, and it is not a resting state in any meaningful sense of the word. And there is the question of the 8 hours. People often cite 8 hours as the requirement, as the number everyone needs, as the thing to aim for. The 8-hour figure is a population average, a center of a distribution, not a prescription. Individual need varies. What the research does make clear is that the architecture of a night's sleep is not uniform, and that where you cut matters enormously. The deep, slow-wave sleep, stage N3, the territory of the slow oscillations and the fact-filing work, arrives early. The first few hours of a normal night are rich in it. The REM-saturated hours, where emotional memory is processed and insight and gist are extracted, arrive late. The final cycles before the natural waking time are almost entirely REM. When you cut the night short, when the alarm is set early or sleep is delayed late, the first thing lost disproportionately is the late night REM. The slow wave work may have mostly finished, but the emotional processing, the procedural refinement, the gist-finding work is still underway when the alarm breaks it off. You may not feel especially tired on 6 hours, but the kind of sleep you lost was not evenly distributed. It was weighted toward the end, and the end is where the REM work lives. This is why researchers and clinicians are careful to say that adequate sleep means not just enough hours, but enough of the right stages, and the right stages require the whole arc of the night. Let us pause here, gently, one last time. Take a slow breath. Let the chest rise and fall without help from you. Notice if you can that the things we have been following together through this night are not abstractions. They are happening in a body very much like yours, in a brain organized exactly the way we have described right now or very soon as you settle and the first slow oscillations begin to form in your prefrontal cortex and sweep backward across the sleeping landscape. The inbox in your hippocampus, whatever arrived in it today, is waiting. The thalamic reticular nucleus is preparing to send its spindles. The glymphatic channels are beginning to open. There is nothing you need to do, nothing to hold in mind or try to remember. The brain has run this sequence before, many thousands of times, and it knows what to do with the night. We have covered a great deal of territory together, and I want to gather a little of it before we say goodnight. Not to test you on it, not to ask you to remember it, just to let it drift past one more time, lightly, like something seen from a window. There was the hippocampus, that fast, fragile inbox. Small and curved and tucked deep in the brain, receiving the day's experiences with urgency and without discrimination, holding them in a temporary, high-plasticity state that is necessary but not safe. That was where we began. There were the place cells in a rat's hippocampus, firing in a sequence along a maze, and then, in sleep, firing in that same sequence again, but compressed to a 10th or a 20th of the original time. The brain hitting its own fast-forward, rerunning the day's experience at high speed while the body lies still. Wilson and McNaughton, 1994, one of the most robustly replicated findings in the field. There was the 3-rhythm handshake, the slow oscillation, rising and falling at about 3/4 of a cycle per second, generated in the prefrontal cortex and sweeping backward. The sleep spindle, a faster burst from the thalamic reticular nucleus, riding on the upstate of the slow wave. And the sharp wave ripple, the hippocampus's own high-frequency signature, nested inside the spindle. Ripple inside, spindle inside oscillation. A clock, within a clock, within a clock, and the memory transfer happening in the narrow windows that alignment creates. There was the rose, the scent of roses piped into a room during slow-wave sleep by Rasch and Born and their colleagues, and the sleeping brain preferentially consolidating the memories that had been associated with that scent during learning. The brain being steered by a cue it received without knowing it received it, targeted memory reactivation. The proof that the process is not merely automatic, but responsive, directable, at least in its broad outlines. There was the conversation we had about REM, about noradrenaline at its lowest point in the 24-hour cycle, about the brain reactivating emotional memories in that low noradrenaline environment and, the theory goes, stripping the raw charge from them while preserving the information. The reason a grief softens overnight. The reason you can eventually remember something painful without being undone by it each time. The overnight therapy that runs in the late hours without your permission or your guidance. There was the insight experiment. Wagner and colleagues in 2004, the hidden rule in the number sequences, the people who slept twice as likely to crack it as the people who stayed awake. The sleeping brain finding patterns and shapes that the waking analytical mind could not locate. There was the old study from 1924, Jenkins and Dallenbach, and the simple finding that has held for 100 years. Waking life erases, sleep protects. The new memories that have nowhere safe to go while the world is pouring more information in. There was the overnight triage, the sleeping brain prioritizing what it had been told to care about, the emotionally weighted and the tested, and the rewarded rising to the top of the filing queue. There was the finger-tapping sequence practiced and then slept on, and the 20% improvement that appeared without a single additional repetition. The offline gain. The skill being refined in the absence of the person doing the skill. There was the 40% deficit in the hippocampus's encoding capacity after one sleepless night. The full inbox, the surface that cannot receive new writing because the old writing was never cleared. There was the glymphatic system, the interstitial space opening by 60% in sleep, the cerebrospinal fluid moving through, the beta amyloid being carried away, and what happens when the shift is skipped, when the protein sits a little longer in the space between cells. The PET scan showing elevated amyloid in the hippocampus and thalamus after a single night without sleep. Not a settled cause and effect, but a recognized risk factor, a mechanism that is coherent and that points in a direction worth taking seriously. You do not need to hold any of this. If one image stayed with you, the inbox and the archive, or the rose scent steering the sleeping brain, or the thought of the three rhythms nested inside each other like something from a piece of music, if one thing settled somewhere quietly, that is already more than enough. The brain will do the rest. Right now, or very soon, your own slow oscillations will begin. Your own thalamus will generate its spindles. Your own hippocampus will begin the compressed replay of whatever today held, moving through it at high speed in the dark, deciding what to send forward and what to release. You did not need to understand any of this for it to work. It has always worked. Long before anyone named the hippocampus, long before Wilson and McNaughton watched place cells fire in a sleeping rat, long before Rasch and Born discovered what a sleeping brain does with a smell, you have been doing this every night. Your brain has always known what to do with the dark. Tonight, it knows this too, and you can trust that. Sleep well. You are safe here, and the night is doing exactly what it is meant to do. Welcome to Sleepy Harbor. You're moored safe in the Sleepy Harbor now. Drift off.